Cool. Hey everybody, my name is Gian Merlino. I'm a Druid developer and a happy new Samza user. I just got finished with switching all of the ingestion stuff at MetaMarkets to Samza about 5 months ago, actually with Alex, who's in the audience. Thanks, Alex. But yeah, so we're using Samza to get data into Druid, and that's for the purpose of indexing these time series streams we have at MetaMarkets and doing cool stuff with them. So I'm going to talk a little bit about what we're trying to accomplish and then how we use Samza to do that. So this is one of my favorite tweets that I've ever seen on Twitter. I think it really speaks to me. I think it's true that you have to sort of, when you're building technology, think about what you're trying to accomplish with that technology, as opposed to just sort of having a good time. Although you still can have a good time. So the problem that we're trying to solve at MetaMarkets is ad tech analytics. We're an online advertising company. So in the world of online advertising, which you may or may not be familiar with, depending on whether or not you have AdBlock installed, there's these ads you may or may not see around the internet. They look kind of like this. If you click on them, which I'm sure someone has done at some point, you get a website that looks kind of like this. And it tries to sell you a mortgage. And then if you actually buy something, that's called a conversion. It doesn't really happen that often, but it does happen from time to time. So what we're trying to do is we're trying to do business intelligence type stuff on this data. So we want to know what top publishers are, top buyers are. We want to do slice and dice. We want to do filters. We want to do aggregates. So business intelligence for ad tech, which is an interesting market because it's a market where even very small companies generate a tremendous amount of data. So we want to offer arbitrary and interactive exploration for this data. Multi-tenancy is really important to us. We want to support thousands of concurrent users. Recency is also really important. So we want people to be able to see and explore current data, and we want to be able to alert on changes in data. And efficiency is also really important. In the online ad world, every individual impression is extremely low value, and it's important that each one can be processed at low cost. So when you're trying to do this sort of business intelligence type stuff, what always happens is questions lead to more questions. You can sort of see what happened on an executive dashboard type of thing, but you want to know why they happened. To find out why something happened, you have to dig into a data set using filters, aggregates, comparisons, and things like that. And the interesting thing is that you cannot really determine all the interesting queries up front. So when you can't determine everything interesting up front, you need a system that lets you explore around. And that's what Druid is. Druid's a project that started at MetaMarkets in 2011, went open source in 2012. Since then, we've been sort of trying to build a community around it. It's designed for low latency ingestion and ad hoc aggregations. And also designed for keeping around a lot of history. So it does real-time ingestion, but you can also keep around years of history and query them at the same time. Like I said, we're trying to build a community. We've got about 90 contributors so far, and it's used in production at a lot of different organizations. So what Druid does is help you explore time series data. The time series, there's a lot of different kinds of time series data, but the unifying feature is there's events happening in a stream, and the events have some sort of timestamp. They happened at some time. And the interesting thing about time series data, and Druid takes advantage of this, is that questions are often time-oriented. So there's use cases in server monitoring. You may want to plot CPU usage over the past 3 days in 5-minute buckets. That's a pretty classic use for time series data. Web analytics, this is sort of the Google Analytics case. Cool. This is like the Google Analytics case. You want to know how many unique users we have today, break it down by various things. Business intelligence, which is what we're doing at MetaMarkets. You may want to know which accounts had large revenue deltas this week compared to last week. And in performance monitoring, which I believe someone's going to be talking about next, which I'm really excited about. You may want to know what the 99th percentile latency is of your servers over the past hour. So these are some stats from our production cluster. We're doing about 500,000 events per second on average ingestion, and about 1 million per second at peak. This is all going through both Samza and Druid. The events per second per core is a Druid number, 10,000 to 100,000 events per second per core. The reason for the range is that 100,000 is what you get in benchmarks and 10,000 what you get in production. Query latency is pretty good. We try really, really, really hard to keep these query latencies down, because when you're doing a sort of interactive exploration type thing, like we're trying to provide to our clients, it's really important to be able to make a query, see their answer, make another query, see the answer, make another query, and sort of repeat that process. So we tune things to get 90% of our queries done in less than a second, 95% done in less than 5 seconds, and 99% done in less than 10 seconds. And this is on a cluster that has about half a petabyte of compressed data in it. It's on about a few thousand cores in AWS. So the way the Druid does queries is through this one weird trick. And that weird trick is time partitioned immutable shards. So the time partitioning is what I was saying earlier. The Druid actually takes advantage of the fact that the data is a time series. The way it does that is it sort of has, as a first class thing in the database, a time index on all data. So you have this time partitioned immutable shards. There's a global index of time interval to shards that the Druid query broker, which is the node you actually hit when you're talking to Druid, it knows which shards are going to have data for which time intervals. And then once a query reaches a shard, each shard contains indexes for fast Boolean filtering. And then once you use those indexes to find out which rows you need to scan, each shard is column-oriented and compressed to make those scans as fast as possible. So the whole idea in Druid is to use the time range of your query and the filter on your query to get to the appropriate rows as fast as possible and then scan them as fast as possible. Then partial results are computed locally on compute nodes and merged hierarchically. So one compute node may be computing results for 1,000 segments, and it'll merge those, and then the entire query may have results from 100 compute nodes, and then those will be merged by a higher level node. Druid ingestion is kind of where Samza fits in. We use Samza as a data integration piece to get data into Druid. So the way Druid ingestion works is you must have denormalized flat data, and what that means is Druid takes JSON, very, very simple JSON objects. It cannot do any stateful processing at ingestion time. So one thing a lot of people want to do is stream joins, and we actually want to do this in the ad tech world. Some people want to do user session reconstruction for web analytics. There's a lot of other useful things that require state, and Druid can't do them. So many users of Druid need an ETL pipeline. And you want a streaming data pipeline because you have this database that supports real-time loads. You want to load it in real time. So I'm going to go through sort of our use case for how we load data into Druid. And I'm hoping that as part of doing that, it'll be something that applies to other kinds of time series data and also potentially other data stores if you're using something other than Druid. This will be sort of how we use it with Samza. So our goals, our input data coming into our system from all of our clients are impressions and clicks and these ID to name mappings. So by ID to name mappings, I mean like you have a publisher, you have an advertiser, it'll say, the impression will say publisher 100, that's actually some name, and so on. So generally the way that this works in the ad tech world is that most of the data comes with the impression, and the click is just sort of like a Boolean that says this impression was clicked or not. So we're getting these two streams in, impressions and clicks, and then we have these tables, these ID to name mappings. The output is enhanced impressions. This is that single denormalized flat stream that's going to go to Druid. So the general sort of steps that we have to do in our ingestion pipeline are first join impressions with clicks. So this adds the field is clicked. So we'll have all the fields that were in the impression, we'll add is clicked, which will be a Boolean, true or false. The next thing we do is look up IDs to names and add publisher name, advertiser name, and so on. Then we do other sort of additions and transformations, like we'll dissect the user agent and pull the browser notice out of it. We may do some geo stuff. We may do other things. I think people usually call this enhancement or augmentation or something like that. We call it looking up because we like to be different. So I'll sort of show what we're doing visually with Samza. So this is what we have. We have impressions and clicks in Kafka, and we have empty database in Druid with nothing in it that we want to put stuff in. And we have a big question mark in the middle that we hopefully want to fill in. So let's look at what we actually have in Kafka. So Kafka's partitioned. What we get in the impression and click topics is not partitioned by a key, it's just partitioned by null. And the reason for that is because then you can still produce even if some partitions are down, which is kind of nice. But the disadvantage of partitioning by null is that you have an impression with the same key as a click, but they're in different partitions. And this is bad because Samza does partition-oriented state management. And we need to get those in the same partition. So the way we do that is with a shuffle job. So the shuffle job reads from two input topics, impressions and clicks, and writes to an output shuffled topic. What that topic looks like, it actually is partitioned by key. And it puts those two data types in the same topic. So you see impressions and clicks in the same topic, and you also see everything with the same key ends up in the same topic. And this is to sort of prepare for the next phase, which is going to be a join. So the join, what that does is, so the clicks are now gone. We're not really interested in clicks unless there's a corresponding impression. So the clicks are gone, and the impressions have a new field, is clicked, true or false. They're also, the type field is gone because these are all impressions. It's sort of implicit. And the way this works is we actually use a state implementation that we wrote ourselves because we were looking at using LevelDB back when Samza still used LevelDB, and the performance wasn't really what we wanted. And so we just made up our own thing. I never tested RocksDB, so I don't know how good that would be. But basically the way it works is there's a buffer of a configurable size. We usually use about 15 minutes. And impressions are buffered for 15 minutes, and clicks are buffered for 15 minutes. And when two come in that match, we sort of emit an output. And when an impression comes in that has no click, we emit one, too, that says is click false. OK, so we have in the join topic this sort of data. The last thing we want to do is enhance it and output it to Druid. So the enhancing is doing the lookups, doing the user agent dissection, all that kind of stuff. We don't write that back to Kafka because there's kind of no point. We just sort of write it. We do that in a Samza job and then write that result directly to Druid. We could write the Kafka if we wanted to. If we wanted to keep things more pure and use Kafka for all inter-service communication. And in that case, we would have an enhanced topic in Kafka that has that enhanced data. And then Druid would read directly from Kafka. This is actually possible. Druid does have support to read directly from Kafka. We just don't do it this way. Mostly because we're really, really, really cheap and don't want to pay for the extra Kafka topic. So operations. One of the reasons we switched to Samza, or actually like the big reason we switched to Samza, is because the operations are really, really good. So I can talk about what we like about it. So the nice things about Samza are mostly operations related. Multi-tenancy is great. There's one main thread per container, which is really cool. It means you can use Yarn's CPU isolation stuff to make sure the containers don't step on each other CPU-wise. So you have this sort of Yarn. We do use Yarn, and so you have these containers. They have a fixed bundle of resources. You sort of get. We give them like a CPU and a half, and I think about 3 gigs of memory, and that's what they get, and Yarn enforces that. The robustness is really good. So there's always going to be slow containers. There's always stragglers. There's always going to be failures. But the fact that the containers don't talk to each other and they only communicate through Kafka means as long as Kafka's working, the containers are completely isolated from each other. Of course, the flip side of that is if Kafka's not working, you have problems everywhere. But just don't get into that situation. I'll talk more about that in a bit. We actually have gotten into the situation a couple times. But visibility is also really nice. So we do multi-stage jobs. So we actually, in that graphic earlier, each of those little boxes in the Samza thing, the shuffle, the join, the enhance was a separate Samza job. We never thought of doing it in one job. I was taking a look at the implementation of the streaming SQL stuff, and it looks like everything is just sort of being done in one job that has a switch, which is kind of cool. Didn't think of that. But I kind of like them in different stages. It means they're even better isolated. And each stage sort of emits its own metrics that are really easy to isolate from each other. So it makes it really simple to see, like, oh, a job's performing poorly. Why is it performing poorly? I don't want to just blindly scale it up. I want to sort of understand what's going on. The other nice visibility thing is you can actually look at what the jobs are sending to each other by just consuming the Kafka topic directly, which is really, really nice for debugging. And we use that a lot when we were developing. State is simple. That's pretty cool. So the state changes, local state changes you make are logged to Kafka. Restoring is handled for you. That's all really cool. We, like I said, implemented our own state thing, and it was pretty easy to do that because it's all single-threaded programming, which is the easiest kind of programming. So that's the good stuff. There's also some ugly stuff and bad stuff, but the list is shorter, so that's nice. Things to watch out for. And these are all things that bit us at various times. Multi-tenancy issues on Kafka is kind of annoying. So Kafka doesn't really have great support for isolating different users. We have one big multi-tenant Kafka cluster that all of our customers are using. And again, that's mostly for cost reasons. It's a lot cheaper to have a multi-tenant situation than isolated resources. The downside of that is unless you're really careful with capacity planning, you can get in a situation where some topic goes out of control, some producer goes out of control and sort of overwhelms the cluster and causes issues throughout the system. Another thing to watch out for is Samza state size, which generally Samza handles large amounts of state really well when the job's running. But when it comes time to restore, it actually has to restore all that state before it can run again from Kafka over the network. That's not super fast. So what we found is if we limit it to a few gigabytes per container, generally seems fine. We did some tests with more than that, and I mean it works, but it takes 20 minutes to start up a job, and that's kind of annoying. Other thing to watch out for that was mentioned previously is that serialization time can add up. That's sort of just a thing that happens in any sort of database or stream processing situation, but it's still true. And the other thing is the default task commit interval is 60 seconds, meaning Samza only commits its offsets every 60 seconds. And that's more or less fine. We actually didn't change that. We're still using 60 seconds, but it can be surprising at first when you restart a job and realize that you get 30, 40, 50 seconds of duplicate data loaded into your database. So we were surprised by that at first and then sort of decided, well, it's probably fine. But it's something to look out for. So monitoring. So we do a lot of monitoring of stuff. We try to be up as much as possible. These are sort of some things that we found were useful to monitor. Kafka partition availability is pretty important. Availability and even more interesting than availability is under replication. That's sort of like an early warning we found. We generally found that if a Kafka cluster has more than 0 under-replicated partitions for like any protracted period of time, that probably means that something is going to break soon. And the nice thing is, at least in our environment, we usually get about a day of warning before anything actually breaks. So it's good to look at that and treat it as the serious issue that it is. Kafka disk usage is really interesting to monitor, really important to monitor. We had an outage that was due to the Kafka log compactor thread failing and then the disk filling up. So monitoring disk usage really aggressively helps with that. Samza consumer offsets, monitoring those is interesting. That's sort of the way that we tell whether a job is scaled up properly or not. The Samza jobs all emit a metric that's I think the messages behind high watermark, and you want to sort of look at that. If it's above a really small number for a period of time, or if it's growing, that's bad. The next two are Druid specific. So Druid's real-time ingestion has currently the way it works, and we're planning on changing this, but currently you configure sort of a real-time window, and it'll accept data in real time for that window, and anything outside that window it'll drop. And most people set that window of like 10 to 60 minutes. So we monitor the Druid drop rate. If we see Druid starting to drop data, that's a pretty strong indication that something is wrong with the pipeline. Usually means we're processing older data than we thought we should be processing. Druid query latency we monitor. Like I said, we're really aggressive about keeping our Druid query times down. And when they get too high, we sort of detect that and try to figure out why. System metrics are sort of classic things, but they're still important. We found that in AWS, network is actually a pretty big issue, bigger than all the others. So we monitor that most closely, but the other ones are important too. And then just event counts at various stages. This is to make sure your jobs are correct and not doing stupid things. It's a really sort of rough check, but it's useful. It's useful to catch bugs. I think that the LinkedIn guys talk about this in most of their Kafka talks, and they call it audit. At least I think that's the same thing I'm talking about. So this is a screenshot of our metrics thing that we use to monitor Samza. This is actually the MetaMarkets product. We're dog fooding it as like an internal monitoring thing. This is all using Druid. So we actually take all the metrics emitted by Samza, go back into Kafka, and then go back into Samza, and then go into Druid, and then you see them here. So the snake eats its own tail. So this is a pipeline that's operating really well. It sort of has events coming in. It has events going out. The word Starfire that's sort of the framework that we use to write Samza jobs. The Kafka offset delta is the consumer messages behind watermark thing. It's pretty low. That's good. The entry lag is how many minutes old data is when it enters the Samza topology. This is whatever 0.11 minutes is, which doesn't seem that big to me. And the Druid success rate is 100%, which is what you want to see. It means that there's not any old data entering Druid. This is a screenshot of a pipeline that's working less well. You can sort of tell it's not doing well because the Kafka offset delta is climbing. So it's starting to fall behind the most recent messages in Kafka. You can also see that once it falls behind a certain amount, the Druid success rate starts to dip, and that's because the data is getting now old enough that Druid is dropping it in real time. So if we see something like this, it's a pretty clear indication that something is wrong, and we either need to scale it up or do a performance debugging, depending on how urgent it is.
When would that occur?
The most common reason is when you don't have enough parallelism. So like you had 4 containers, but you need 5. In that situation, the system just sort of keeps working, but falls behind. Yeah?
Have you ever tried Storm?
Yeah, so we were using...
How do you support multi-tenancy? Which kind of framework are you using?
So we did try Storm. We were using Storm before Samza, and most of the reason for switching was that operational stuff. We had a lot of operational issues with Storm. For multi-tenancy, we're using the Yarn runner, and so we're using Yarn's memory isolation, and we pulled in a patch from some Jira that I forget. I'm not sure if it's in a release yet, but at the time we pulled it in, it wasn't. That does it does C groups based CPU isolation.
What kind of other application, core application are you running side by side with your scripting application?
None. So our Yarn cluster is just running Samza.
Why are you creating multi-tenancy?
Uh,
In my understanding, multi-tenancy is one is running Hadoop, the other is running Spark.
Right.
And so many, only one customer. So that's multi-tenancy.
Right. So we're
You
not.
only have one tenant. That's not a multi-tenancy.
Yeah. So we're not doing that level of multi-tenancy. When I say multi-tenancy, I mean different stream processing pipelines for different customers of ours. So we, in our world, each of them has their own dedicated stream processing pipeline, and it's important to us that they don't affect each other. But yeah, it's only one kind of application, but there's many instances of it running.
That's like a unicorn.
A what?
Unicorn.
Yeah. So it's all Samza jobs in the cluster, but a lot of different Samza jobs.
By the way, how do you deal with traffic spike and things like that? In terms of both software architecture and infrastructure level, how do you deal with traffic spike and try to reduce cost or improve performance, something like that?
So the question was, how do we deal with traffic spiking? Are you talking about query traffic or like ingestion traffic?
Peak time, on-peak time, in off-season, in low season, high season, things like that.
Yeah. So we don't do any sort of automatic adjustments. We provision for peak load and sort of leave it there. We're hoping to change that this year. Actually, yeah, we're hoping to change that this year.
Yeah, but you definitely know your traffic pattern. You know it in advance.
We can try to predict it. Yeah, I mean it's generally It's not super random.
Yeah, but it's also a monitoring problem.
Yeah.
Forming a loop.
Yeah. So I mean, we have enough data to predict it. It's more of a question of
Again, it's
having a reasonable predictor.
yeah, it's a bigger data problem.
It is, yeah. Yeah, it is. That's why we're doing the peak thing right now. Okay. So the last thing I want to talk about is, and also apologies in advance if this isn't the last thing, is reprocessing. So I feel like when you're designing a streaming ingestion system, finding some way to handle reprocessing is really important, unless you just don't care at all about historical data, which some people don't. Some people have purely sort of right now operational use cases, but I think most people care to a degree about historical data, and therefore reprocessing is important. So why is reprocessing important? Well, you could have bugs in your processing code, and you're going to want to reprocess your data to sort of with a fixed version of your software. You can have imprecise streaming operations. So one thing that we do is when we do Samza, we have a shorter join window than when we do a sort of a batch process. And the reason for that is because of that sort of state thing. We're trying to keep the state to a amount where restarts happen in a reasonable amount of time. The third reason is software limitations. So in the open source world, you have Kafka and Samza, which can both generate duplicate messages, which if you have an idempotent database, that's fine, but Druid's not idempotent. Also, Druid streaming ingestion is best effort. So it's not even at least once like Kafka and Samza are. It's sort of, it tries as hard as it can, but it may have duplicates and it may drop a little bit of data. In practice, this happens when you have network issues or machine failures, so it's pretty uncommon, but it can happen. And if you care deeply about correctness, then you have to deal with that. So the way that we deal with that, and a really common way of dealing with that, is a Lambda architecture. So I'm just going to talk about that for a second. That's sort of a hybrid batch streaming data pipeline. Common batch technologies are Hadoop and Spark. Common streaming technologies, Samza, Storm, also Spark. Apparently Spark does everything. Advantages of a Lambda architecture, of this hybrid batch real-time thing. It works as advertised. I mean, it does what it says it does. Works with a huge variety of open software. I think that's one of the reasons why this sort of architecture is so popular. And also specifically to Druid, Druid has a Hadoop indexer that can do a batch replace by time interval, which is a really nice primitive for doing a Lambda architecture type thing. You can sort of take a time window and say, okay, this time window, I have data in Hadoop that I want to sort of replace my real-time data with. And Druid can do that. Disadvantages are pretty annoying, which is why I hope that Lambda architectures are not with us forever. You need code to run on two very different systems. So if you're running Hadoop and Samza, for example, those are very different systems. The operational characteristics are very different. You're basically doubling your workload as far as operational issues and performance tuning. Also, maintaining two code bases is perilous. You have productivity loss, you have code drift, where the two code bases are doing different things, and difficulty training new developers. You have to train them in two code bases. We actually have so many pipelines. This was such a problem for us that we developed a framework to sort of write once, run two times. But I feel like that kind of investment is substantial enough that we only made it because we had so many pipelines. So in our world, our Lambda architecture looks like this. So we have this add data coming into Kafka, being processed by Samza and written in Druid. We also have, I hope that's the logo for S3. I think it is. We have Kafka data going into S3 because we're in AWS. That S3 data is being read by Hadoop and then loaded into Druid using that batch replace operator. And we run this nightly, basically, automatically. There's also a Kappa architecture. It's alternative to Lambda architecture. I don't really have any experience with this, and I don't know anyone that runs it in production other than, I think, LinkedIn, maybe, I'm assuming. Anyone can confirm that? Who knows? Anyway, it was written about in a blog post by Jay. It's a pure streaming architecture where you reprocess data by replaying the input stream. The really nice thing about it doesn't require operating two systems. The kind of less nice thing about it is it doesn't overcome those software limitations that I talked about earlier, which, at least in our view, are substantial enough that we're not using this in production at metamarkets yet. Although it would be nice to not have to maintain two systems. So the final thing I want to say is do try this at home. Most of the things I talked about are open source. The sort of cornerstones of what I've talked about are Druid, Samza, and Kafka. They're all open source. Also the glue between them, which in a lot of cases is a substantial time investment to build. A lot of that's open source too. So in the way that we do things, where we push directly from Samza to Druid, that glue is Tranquility. You can use Camus to load from Kafka to HDFS, or this thing called Ccore, which is Pinterest open source, to load to S3. And then once it's in Hadoop, the Druid Hadoop indexer can index it. There's also the style of architecture where you load directly from Kafka into Druid, and in that case, Druid comes with a Kafka connector. So what I hope you take away from this all is that you should consider Kafka for making streams available to your applications. It's really good at that. You should consider Samza for streaming data integration. I think it's really good at that too. And you should consider Druid if you want to do interactive exploration of streams. Metrics. Metrics are really important. They're the only way you can operate a distributed system in production with any sort of uptime. And the last thing is, if you're interested in historical data at all, you should have a strategy for reprocessing. Thanks, guys. Any questions?
You'd mentioned the at-now type of queries. Do you have, where you have to have the right-hand side of your time intervals is right now?
Mm-hmm.
And so you want to be faster than 1 second latencies? Are you mirroring into another key value store? Or?
So the question is, how do we handle the sort of real-time queries where data is getting loaded into, where data is available for querying as fast as possible? So we do that with Druid. Druid, I didn't get into it in this talk because I didn't have time, but Druid has actually two pieces to it. It's got a historical data piece and a real-time data piece. Yeah, well, it doesn't. It actually can do the exploration in real time. So if you're interested in that, there's a lot of sort of videos and docs on the internet about how that works. You can look up Druid real-time indexing, but it's basically a sort of compromise form that's a compromise between write optimize and read optimize that's used in real time to support the same exploratory queries as we do in historical using the totally read optimized form. So those are not immutable.
You had mentioned when you were running Kafka that operationally you saw that if certain Kafka partitions were not being replicated quickly enough, that sort of indicates that a failure is going to happen soon. How do you deal with that scenario? How did you recover from it? How do you fix that when you come across those scenarios?
Right. Add more brokers. Add more brokers. Yeah, add more brokers. Yeah, or if you have a hotspot in your brokers, try to move partitions around to get rid of the hotspot. But yeah, it means you need more hardware. Or something's not tuned well, but
what's the reason why that's not replicating? Is it just
it's usually because either CPU or disk or network is pegged on one of the brokers.
Or a broker died.
Yeah, or a broker died.
So you mentioned writing directly to Druid instead of through Kafka. Pardon me. How is that working out? Because in my mind, that would DDoS Druid. It could. It also could bottleneck your stream processing, because if you're not writing to Druid fast enough, I'm assuming the ingestion rate is less than the rate at which Samza can process.
So I guess the simple answer is that the rates can be the same because both are horizontally scalable. So you'll have as many Samza containers and as many Druid partitions as you need. So yeah, in Samza you're adding containers, in Druid you're adding partitions, but they both scale out. It does. So if you do have a scaling issue in Druid and you need to add more partitions, but you haven't done it yet, that will back up the Samza job. In our case, that doesn't really matter because the only thing it's doing is writing to Druid. And so it's not really hurting anything if it slows down a bit.
But what if there's a spike and it will cause multi-tenancy issues in Druid? Right? The queries are coming in and the ingestion is just going crazy.
Right. So for multi-tenancy issues in Druid, we have inside Druid there's resource isolation between ingestion and querying. So Druid will try to ingest as fast as it can, but if it has to make a choice between ingestion and queries, it'll let the queries go through.
Can you comment a little bit about the custom store you wrote and whether it makes sense to like open source it, or is it specific to your use case? It sounds generally useful.
I've been wondering that myself, whether it makes sense to open source it. It's a stream joiner that is, you have, I mean, what it looks like is you have a log, and then you have an index into that log, and that's sort of, those together make an append-only multi-map. And then there's this part for like evicting old sections of it, so you can sort of like expire large chunks at the same time. So it's good for stream joining. I took a lot of shortcuts in implementing it such that like it's not very configurable. Like it works and it's fast, but it's not like if you want to do things exactly the way that we do it, it would work fine.
Timur.
Yeah, I guess my other answer to that is if anybody actually wants to use it, like come talk to me, and that would maybe convince me to put it over the edge.
2 more questions. You get to go second or third.
What kind of operator, the most complex operator you are running, during stream processing? I believe most of your operators are just an aggregator or things like that. It's very simple, right? Do you have any sort of complex operator operating on your stream? That's one question. And the other is also a shorter question. Do you adopt any sort of data lake so you store your streaming data from day one and you never delete any kind of data? It's possible, right now.
Right. So I'll answer the second one first. So you asked about data retention for streaming data. For some data sets, we store all the raw data going back to the beginning of time. For some, we delete it after a amount of time. That mostly depends on what our agreement looks like with the particular client. What was the other question? I forgot. Oh yeah, you asked if we had any complex operators as opposed to simple operators like transforms or aggregates. The one complex operator we have is the stream join. And the stream join operator is fairly complex. It's about half the code base of our Samza stuff, and the other half is everything else.
If you cannot finish it within your real-time, your definition of real-time, because different people have different kind of definition of real-time. How do you do that? If you cannot accomplish within real-time, 7 seconds or 7 minutes, whatever.
Right.
So how do you adjust your window, or you scale out your architecture? I'm not sure whether you're going to add hardware level, software level, or something to add into it, or a combination of different approaches. How do you do that?
We generally scale out because we generally have. If we're doing a join, it's because we have to, and there's only so much we can shorten the window before getting things not joining properly. So scaling out.
Can you accomplish it in real-time fashion?
Yeah. It's we found similar things about Samza to what you said in the previous talk, which is that it scales pretty linearly and Kafka scales pretty linearly. So we haven't hit a ceiling yet of what cannot be done in real time. It's just a matter of how much hardware you want to use, at least in our experience.
Yeah, joining is not that complicated. If you want to do very complicated machine learning operator,
Yeah, we're not doing anything like that.
you could do that.
Yeah, no, the joiner is the most complicated.
I guess since it's the last question, when you when you decorate your events, do you do any sort of caching in your stream processing layer? How do you actually get those? Do you make API calls outside, or how does that work?
Right. So the stuff that we use for decorating is usually like a little table, and they're usually no more than a couple hundred megabytes, so we have the memory on every node. We keep them in S3, and the first thing the stream tasks do when they start up in their init is they download all those things.
Thank you very much.
Sure. Thanks.